And with that, I would like to welcome you again to this webinar hosted by us at Swedish Life Cycle Center. And this webinar is, as I said, a part of the project Incentives for Energy Recovery in LCA for Plastics, which is funded by the Swedish Environmental Protection Agency. And this webinar is also part of a series of webinars that Swedish Life Cycle Center are giving as part of the project Innovation Cluster for the Life Cycle Perspective. And we will now listen to Thomas Ekvall, who will give an introduction to the project and present the methods. After that, we will listen to Maja and Marie, who will present the calculation and the results from that. And Thomas will then come back and present the discussions and the conclusions. So now, Thomas, I will stop sharing and leave the floor to you.
Thanks a lot. Yeah, as this project is about energy recovery, you can from the title, but the focus is, the starting point is really in modeling of recycling. When you recycle a material, you need both, to recycle a material, you need both the supply and the demand for secondary material. So you need two separate actions. One is to recover material in the life cycle for recycling, and the other is to use the recycled material in a new product. In an LCA, we typically assess each of these actions separately, and it's a little bit like assessing the action of clapping one of your hands. When you do that, you find that you're most likely to just hit air. You might also hit an object or a person in front of you, and the likelihood that you will hurt yourself or someone else is much greater than the likelihood that you will produce a clapping sound of an applaud. So you shouldn't clap one hand, clap your right hand, and of course not your left hand either. So, and the result is there will be no applaud. And similarly, when you assess separately the action of recovering a material for recycling, there might be no recycling because the LCA might indicate that you should send the material to energy recovery, even if recycling really produces the most environmental benefits. So this is the background of our project, and I'll start sharing. So can you see my presentation? No, not this.
It looks good.
Thank you. So this webinar is about this project Incentives for Energy Recovery in Plastics LCA, and we focus on low density polyethylene and only on climate impact, and the focus is also on the circular footprint formula that is part of the product methodology for product environmental footprints. But the arguments and analysis is applicable also for other combustible waste flows and for many other methods for modeling recycling and waste management in general. It's a pilot project in the sense that we only focus on one material and one environmental impact, but also in the sense that we use easily available input data for our calculations. It's funded by the Swedish Environmental Protection Agency and coordinated by Maria at the Swedish Life Cycle Center. And I'm responsible for the methodological parts of the project, and Maria and Maja, who you will hear later, have made the calculations together with their colleagues at IVL. So the risk of having an LCA indicating that you should send the waste to energy recovery instead of recycling occurs when you have an environmental benefit from both processes. And this is a hypothetical case where you have a combustible waste and you get an environmental benefit from recycling and also from energy recovery, although the benefit from energy recovery is smaller. ER here is the environmental burdens of the recycling process, and E star V is the avoided environmental burdens of virgin production of the material. ER is the environmental burdens of energy recovery process, the waste incinerator. And E star E is the avoided environmental burdens of the substituted energy. So in this case, recycling gives a greater environmental benefit, and you should send the waste to recycling. But if you apply, if the waste is a plastics and you apply the circular footprint formula, you assign only about 45% of the environmental benefits of recycling to the product that generates the waste. So if you have a product and you're considering whether to send it to recycling or to energy recovery, to incineration, you find that you will get a greater credit if you send the material to the waste incinerator than to recycling. So you get an incentive for sending material to energy recovery, hence the title of the project. A here is a material dependent factor in the circular footprint formula, which for plastics is 0.5. And the Q is the quality of secondary material and primary material. And the default value for plastics is that the quality of secondary material is 0.9, 90% of the quality of the primary material. You also have in circular footprint formula factor B for modeling energy recovery, and this in theory can be used for assigning only part of the environmental benefits and burdens of energy recovery to the waste. But in the default value of B is 0, which means that the full environmental burdens and benefits of energy recovery is assigned to the waste in the circular footprint formula. If you use another method for modeling recycling, this method is also likely to divide the environmental benefits of recycling between the product that generates the waste and the product that uses the secondary material. If you use a 50-50 method, for instance, only half of the environmental benefits of recycling is assigned to the product that generates the waste. So what can we do about this problem? I mean, it is a problem because the LCA results for the plastic product will in this case indicate that you should send the product to incinerator, even though recycling is the better option for the environment. So the LCA gives an incorrect incentive. And what we've done in this project is that we focused on the modeling of energy recovery to see if we can somehow balance this, make this balanced, a more balanced and accurate, balanced calculation, which gives more accurate indications of what to do with the waste. And we have tried two ways. One is to question the environmental benefits of energy recovery. In an LCA, you often assume that when you send a waste to incineration with energy recovery, you will get energy from this, and this energy will substitute other energy of heat and electricity. But this assumption is simplistic, because waste incinerators are typically used more or less to their maximum capacity. So in the short term, what happens when you send a waste to the waste incinerator is that some other waste will not fit in the incinerator, but end up somewhere else, and you will not get more energy from incinerating the waste flow that you're studying. So we looked into that, and then there was a question of factor B. Maybe we can find a basis for estimating factor B in a way that makes it not 0, but something higher. So first we looked at the benefits of environmental benefits of changing the waste flow of low density polyethylene to the waste incinerator. And as I said, the waste incinerator in Sweden, at least, they are more or less fully utilized, whether we send this LDPE waste or not. And the capacity is often, not always, but often in terms of the energy flow. So if we send LDPE to the incinerator, another waste will not fit there, and the waste that will be crowded out has the same energy content as the LDPE. We have in Sweden an overcapacity of waste incinerators. We have capacity to incinerate more waste than we have domestically. So what we do to utilize the waste incinerators is that we import rather large amounts of waste from other countries, combustible waste. This waste import is a misleading term, because we of course take a gate fee for treating the waste. So it's rather an export of waste treatment services. But it's called waste import. And so the LDPE waste, if we increase the amount of LDPE in the incinerator, we will be likely to reduce the amount of imported waste, and this waste will end up somewhere else in Europe. And we have made at IVL studies investigating how this could affect the European waste management system, but it's highly uncertain what will be affected in the end. And that means that the environmental impacts of incinerator waste and the environmental benefits are highly uncertain. What we do in this study to illustrate this uncertainty is to use 2 scenarios, assuming that an increase in LDPE waste incineration in Sweden will result in increased landfill somewhere in Europe, in a modern landfill with landfill gas extraction. And in the other scenario, we assume that what is affected is the incineration somewhere in Europe, incineration with electricity production. So this was one attempt to make the LCA give more correct indications, and the other attempt focus on factor B. In the long run, waste incinerator capacity can be changed. It's not fixed, and assuming B is 0 is equal to assuming that the waste incinerator investments are driven by the amount of combustible waste. And this assumption is also incorrect, because we invest in waste incinerators in Sweden, although we don't have domestic waste enough. And if we look at the European perspective, a lot of combustible waste is still put at landfills. So investments, so this quantity of combustible waste is not driving, is not automatically driving the waste incinerator capacity investments. What does drive investments in Sweden, because investments have been made even though we have an overcapacity already, is the economy of waste incinerators. It's a good economy, although they are expensive to build. There is very good economy in driving them, because you get paid for accepting the waste, and you get paid for selling the electricity and heat. So if it's the economy that drives the investments, then we can use the two sources of revenues as a basis for estimating B. B is then the share of the driving force for the investments that is caused by the energy recovery, by the energy sales. And V here is the economic value of the gate fee and the energy respectively. For Sweden, an estimate was made several years ago, or data were collected several years ago, that ended up with finding that slightly more than half of the revenues of waste incinerators were from energy sales. And rounding those numbers, we find that we can use B as B.6 as a tentative value for Sweden. But this will vary between locations, and it will also vary over time. So that is the two methods that we're using in the study to see what we can do about the problem that LCA sometimes give incorrect incentive to send waste to incinerators rather than recycling. That was the first part of my presentation, of our presentation. Thank you.
Thank you, Thomas. Maria and Maja, please start your presentation.
Yes, thank you, Thomas. My name is Marie Gottfridsson, and I'm working together with Maja Nellström at IVL Swedish Environmental Research Institute. As Thomas said, we have been working with the calculations in this project, so we are going to present our work and the results. So we have done a case study where we calculate the climate impact of 3 different waste management options for LDPE. We have mechanical recycling, chemical recycling, and incineration in Sweden. In this study, we're using the functional unit of 1 ton waste LDPE. We are both looking at fossil and renewable LDPE. And as Thomas also said, we have 2 different scenarios for incineration with energy recovery. The 2 waste management options, the 3, are compared with 4 different methodological approaches, and we will describe them further later. And our calculations are made with the CFF formulas for mechanical recycling and incineration. And now Maja will start talking about our model.
When modeling the waste management options, we use the Gabi software model with databases from ThinkStep, Sphera, and Ecoiment. And for the two European scenarios, we use the VAMS model, which is an LCA model for waste management developed by IVL. And some key general assumptions that we made are that the recycling and incineration processes are assumed to be located in Sweden, and we therefore use data sets relevant for Swedish conditions. Transportation within Sweden was not included in modeling, since these distances are assumed to be relatively short, and they are also assumed to be similar within the different waste management routes. The emissions of biogenic CO2 are assumed to be climate neutral and therefore do not affect the climate impact results. And also for district heating and electricity, we have used Swedish average data.
So this is a basic overview of our model for the chemical recycling. We have included the steps sorting and baling. We have washing, melting, and granulation. We also include the avoided production of virgin LDPE. And we are not including the collection of plastic waste since it mainly consists of transportation. And as Maja said, we assume that this mechanical recycling process occurs in Sweden, which means that we are using Swedish average electricity mix. And for 1 ton LDPE waste, we get 1 ton recycled LDPE. And this recycled polymer is assumed to replace 1 ton virgin LDPE. And for the chemical recycling, we are using a model for pyrolysis. And here we include the sorting and baling. And in the pyrolysis plant, we have a washing and melting process and the pyrolysis oven. Here we also include the avoided production of naphtha. And we get the pyrolysis products, coke, syngas, and pyrolysis oil. And we assume that this pyrolysis oil will replace naphtha, and we also assume that the coke and syngas will be incinerated and generate CO2 emissions. And in our model, we get 720 kilograms of pyrolysis oil per ton recycled LDPE.
And for the incineration with energy recovery, this includes incineration of the plastic waste, where the generated energy is used for electricity and district heating. And when we calculated the climate impact for the European scenarios, we used a modified version of the CFF formula, which you can see in the slide. And in this formula, EER is the specific emissions from the avoided energy recovery of imported waste, and ESC is the scenario-dependent specific emissions from the alternative treatment of the imported waste in a European country other than Sweden. And Thomas has already mentioned these scenarios, but just to give you a reminder, the European incineration scenario involves increased incineration of plastic waste in Sweden, which leads to reduced waste imports and to more waste being incinerated with electricity production in another European country. And for the European landfill scenario, increased incineration of plastic waste in Sweden leads to reduced waste imports, which then leads to an increase in disposal of untreated residual waste in another European country.
As I mentioned before, we are using 4 different methodological approaches for the 3 waste management options. And these are simple substitution, And we have a default PEF approach where B equals to 0. We have the PEF calculations with B equal to 0.6. And we also have the adjusted PEF calculations, which means our scenarios, with a European systems perspective on Swedish incineration. So for our different approaches, we are adjusting the CFF variables according to this table. For example, for simple substitution, we assign the full benefit from substituting virgin material to the LDPE that is sent to recycling. Here we set factor A to 0 and factor B to 0.
Yeah, exactly. We will present the results now for the 4 approaches, where we compare climate impact for the case of fossil and renewable LDPE, and the values are given in CO2 equivalents per ton LDPE. So these are the results for the approach simple substitution for both fossil and renewable LDPE. And this is the approach that, as far as we know, reflects the real climate benefits of recycling and incineration. And in the figures, you can see the climate impact for mechanical recycling of fossil LDPE has the same value as for mechanical recycling of renewable LDPE. And you can also see the climate impact for chemical recycling and incineration with energy recovery of fossil LDPE is greater than for the case with renewable LDPE. And the negative values obtained for chemical recycling in the renewable LDPE case, these negative values is due to credits for production of naphtha, and the negative values for the incineration of renewable LDPE is due to the credit for production of district heating and electricity. And we move on to the results for the approach PEF default, where the B value in the CFF formula is, as Marie mentioned, set to 0. And in these figures, you can see the same trend applies as for the simple substitution case. The climate impact is the same for mechanical recycling when comparing fossil and renewable LDPE, whereas there is a difference in climate impact for chemical recycling and energy recovery when comparing fossil and renewable LDPE.
So here we have the results from the PEF calculations with B equal to 0.6. And again, to the left you have fossil LDPE, and to the right you have renewable LDPE. And as a reminder, for the renewable LDPE, the emissions of biogenic CO2 are assumed to be climate neutral. And finally, we have the results for the PEF scenarios. We have energy recovery, European incineration, and European landfill. And again, to the left, we have for fossil LDPE, and to the right, we have renewable LDPE. And these scenarios are calculated with the WAMPS model, as we said before, and the replaced energy is assumed to come from natural gas. And these scenarios and pictures will be discussed further by Thomas in the next part with discussion and conclusions. Thank you.
Thank you, Maja and Marie. And Thomas, welcome back.
Thanks. I hope you can see my presentation again.
It looks good.
Thank you. So these were the results that Maja and Marie showed. for simple substitution. And with simple substitution, you include the full environmental benefits and burdens of recycling as well as energy recovery. So here you see our estimate of what are the actual environmental benefits and burdens of recycling and energy recovery. And for fossil LDPE, you can see that there is no net benefit, but a solid net burden of energy recovery, because LDPE emits a lot of combusting LDPE emits a lot of fossil CO2, and the heat and electricity replaced by energy from LDPE is, in our calculations, the average Swedish electricity and average Swedish district heating, which are rather low impacts on the climate. So the benefits of energy recovery is small, but the burdens are great for fossil LDPE. Chemical recycling, you can see that you also have some emissions of fossil CO2 from the pyrolysis and so on, and you replace oil, and you do not replace plastics, but oil, which means that the benefits of chemical recycling is also rather small. So mechanical recycling is where you get the solid benefit for both fossil and renewable LDPE. And since there is no net benefit of energy recovery from fossil LDPE, there is no risk that the LCA results will indicate anything else than that mechanical recycling is a better option. So I will not discuss those results anymore. Where we have the risk is for renewable LDPE, because there you have a net benefit both from mechanical recycling and from energy recovery. And you can see that with simple substitution, the results will indicate that you should send the plastics to LDPE to recycling still, because the benefit is greater. If you apply the default PEF methodology to the left here, you reduce the net benefit of recycling by 55%. But you still have the results will still give the correct indication that you should send the material to recycling, because the benefits of energy recovery is so small, because we assume the average district heat and electricity to be replaced. If the energy replaced has 40%, more than 40% climate impact in addition to the average, then the PEF results would indicate that you should send the waste to energy recovery, to incineration. And as indicated in a comment by Miguel while Maja and Marie were talking, this is sometimes a correct indication. You have kind of the correct results in the simple substitution, where you have the full benefits of both recycling and energy recovery. And if the energy substituted at the incineration has 3 times greater climate impact than the average Swedish electricity and district heat, then the net benefit of energy recovery is actually better. So with the data we put into, you will get correct incentive that mechanical recycling is a better option. If the energy substituted has 3 times more the greater climate impact than the average Swedish heat and electricity, then the energy recovery is actually the better option. But when the climate intensity of the substituted energy is between 40% and 200% higher than the Swedish average, the results will indicate, the PEF results will indicate that you should send the waste to incinerator, even though recycling is the better option for the environment, for the climate. So that is when you can have get a wrong incentive from the PEF results, assuming the rest of our data are correct and so on, calculations. So, and then we tried by changing factor B. And then factor B reduces the benefits and burdens of energy recovery by 60% if we use set B as at 0.6. And then the burdens and benefits of recycling is reduced by 55% in the calculations, and the burdens and benefits of energy recovery is reduced by 60%. So the reduction is almost the same. The proportions of results are the same. And there is almost no risk of an incorrect incentive for waste polymers. Because this is a bit of a lucky coincidence that that PEF reduces, PEF with B.6 reduces burdens and benefits of recycling and energy recovery by almost exactly the same amount. It is a bit of a lucky coincidence because B will vary over time and it will vary between locations. And A and Q, that is the basis for modeling of mechanical recycling, will vary between materials. So it makes using our approach for calculating a value of B and using that in the PEF calculations makes the PEF calculations more balanced in the sense that only part of the environmental benefits and burdens of recycling and recovery are accounted for in the LCA of the product that generates the waste. But it will not always give correct incentives. The LCA will not always give correct incentives. For textiles, I expect that you will often have get wrong incentives. So the other approach we used were the scenarios, and as you can see to the left here, when scenarios are applied to the LCA of renewable, to the study of renewable LDPE. In one scenario, the environmental benefits in the European incineration scenario, the environmental benefits of energy recovery is greater than for mechanical recycling, and in the landfill scenario, there is no benefit at all. So the conclusions will be unclear in this case whether you should send material to recycling or to energy recovery, unless you can find good arguments that one of these scenarios is much more accurate than the other. So factor B makes the equation, the PEF circular footprint formula, more balanced. So applying scenarios in it makes it account for more of the uncertainty, but also makes it more difficult to draw any conclusions. That was the two methods we tried. But I've said several times that the simple substitution shows the actual estimated, our best estimate of the actual environmental benefits of both incineration and recycling. So why not use simply a substitution in the LCA? After all, this is what is often called the end of life approach, and it's a very common approach to modeling recycling. The problem is that this approach, end of life approach, makes no difference between input primary and secondary material when used as input to a product. So you get no incentive for using secondary material. And while this might be okay for metals and some other materials, it's a problem for textiles and might also be a problem for plastics, where you really need to stimulate not only the supply of secondary material, but also the use of secondary material. Then the LCA need to give an incentive to using the secondary material. And the end-of-life approach fails to do this. Unless you combine this simple substitution at the end of this life cycle with giving credit for using a secondary material in the beginning of the life cycle, so you have kind of double credit for recycling. You have the scrap secondary material coming without burdens from earlier life, and you still get the substitution in the end. Then the results will, LCA results will give an incentive both to use secondary material and to recycle it after use, when recycling is the better, environmentally better option. Problem is that with such double counting of the benefits of recycling, you will get absurd results in, for instance, a product produced of steel, a steel product produced from scrap that is recycled after use. That will not indicate that you have zero use of iron ore, but that you have a large negative use of iron ore in such a product. And that you should, to save iron ore, you should produce as many of these products as possible, whether you have any use for them or not. That's the main problem with this solution. A third solution is to stop assessing the supply of recycled material separately from the use of secondary material, but jointly assess the supply and use of secondary material. You can do this, for instance, when you're making an environmental assessment of recycling as such. You can also do this when you have a case of closed loop recycling, or when the inputs and outputs of secondary material balance each other precisely. But when you have a net outflow or net inflow of secondary materials, you have the problem of deciding where to assign the environmental benefits of recycling. So in some cases, it's possible to jointly assess the supply and use of secondary materials, and it's like jointly assessing the coordinated action of clapping your hands, and there will be an applaud, and the chances that there will be recycling when recycling is good for the environment will increase. It's not always possible, but my recommendation is that when it is possible, avoid the allocation problem by jointly assess the supply and use of secondary materials. This is also in line with the old recommendations from CETAC Code of Practice that you should, when possible, study the unallocated system. That's all for now, and I think it's been a very interesting projects and thought-provoking for myself, because I used to think that as long as you model the foreseeable consequences of sending a material to recycling, then you're fine, and I don't think that anymore. And if there are more people thinking that I used to do, there will be, I expect there might be several questions and comments. So thank you.
Thank you, Thomas, and thank you, Maya and Marie, for your presentations as well. Thank you for watching this webinar that was part of the project Incentives for Energy Recovery in LCA for Plastics. The project was funded by the Swedish Environmental Protection Agency, and this webinar is also part of a series of webinars that is hosted by Swedish Life Cycle Center. Follow us on social media, Twitter or LinkedIn, or sign up for our newsletter to make sure to not miss any invitations to our upcoming events.